Okay, we're back. And what I'd like to do is to continue the discussion about convolution in 1D and in 2D. In 1D, we talked about convolution in our signal processing sense when we were doing sampling. We call it a sliding window dot product. In 2D, it's still a sliding window dot product with a difference, and the difference is it's a two-dimensional matrix instead of a one-dimensional matrix. Other than that, there's no particular difference. And the reason we like, to think in terms of the convolution is because we can do filtering with it. But one of the problems that we have when we have a little window that's traveling across an image is that we've got this quadruply nested for loop, and it takes a very long time. It's very time consuming. Thankfully, there's I'll call it breakthrough, biggest, most important algorithm of the 20th century, some have said, and that is fast Fourier transforms. And fast Fourier transforms are good because they let us do convolution fast. So instead of doing quadruply nested for loops, we can employ the convolution theorem. Dun, dun, dun. Entering in the convolution theorem, one of the most important theorems that you will learn in this class, we find that convolution in the spatial domain is equivalent to multiplication in the frequency domain. And what that means is if I can take a Fourier transform on an image, I can go into the frequency domain, then I can do a straight multiplication between the image and some frequency domain based filter, and then I can take the inverse Fourier transform and get my filtered image. So think about it a different way. Let's assume you're in the frequency domain and you decide you want to build a low-pass filter. Well, that's easy, right? Because now if you know that you can hear from 0 to 20 kilohertz, or maybe, let's say 12 hertz to 20 kilohertz, if you want to build a low-pass filter and you know that the low-pass filter has a cutoff of, let's say, 20 kilohertz and a half, let's call it 10 kilohertz, then what you can do is you can say anything under 10 kilohertz we let through. Anything over 10 kilohertz we turn to 0. And then after that you go back from the frequency domain into the time domain, and now you've got your original signal without any of the frequency components above 10 kilohertz. So your little low-pass filter was pretty trivial to implement once it was in the frequency domain. You just made a little, we'll call it a step function, whose knee occurred at 10 kilohertz. Multiply it by your input signal, then take your inverse Fourier transform to go back into the time domain, and voila, you've got your filter, your frequency domain based filter. Good deal. So you can do the same thing in 1D that you can do in 2D, using your Fourier transform to go into the frequency domain, doing your multiplication, and then doing the inverse Fourier transform, and blammo, you've got your convolution. Was that a good explanation? Did people sort of follow that basic idea? So here is the convolution on the left, and now here's the multiplication on the right. And what the symbol on the left, the asterisk, that represents the convolution, and the little dot between the big F and the big H, that represents the multiplication. So you can do a piecewise multiplication on the two-dimensional array of F and H, and then do the inverse Fourier transform, and it's equivalent to the convolution. So what it says is multiplication in the frequency domain is equivalent to convolution in the spatial domain. The inverse is also true. This is an analytic statement. If you were to do convolution in the frequency domain, it would be the same thing as multiplication in the spatial domain. Why you'd want to do that, though, I'm not sure. But this is how you would write that. it's symmetric. It's true both forward and backward. So now we can have a looky-loo and see what happens. Here we have this little white dot for the H matrix. We'll do the convolution and get a nice blurry signal. Now, if you do the frequency domain of the peaches in the upper left, you get this interesting looking pattern. If you multiply it by the frequency domain version of this little white dot, which looks kind of like a cloudy pattern, you get another frequency domain output. But when you do the inverse of the right-hand side, you'll get what's up in here. That is, if you do the inverse two-dimensional Fourier transform. The convolution is taking this little H matrix and sliding it across the image matrix with wraparound, computing each pixel individually by doing the piecewise dot product and then summing together all of the numbers, and then moving it by one pixel and doing it again, and moving it by one pixel and doing it again, and doing it for as many pixels as you've got. That's what the convolution is doing. So it's a very time-consuming operation, and it's doing it with wraparound, which means when you slide off the edge, it pops up on the other side.
So what is it? That last image is just blurry.
That's the result of the filter, a low-pass filter, where the high, I'll call it high-frequency components that made up the edge have been blurred. If you had inverted this filter by putting a black dot in the center and wall white around it, then you would have had a high-pass filter instead of a low-pass filter, and that would be an edge detector, because then it would say yes wherever it saw a sudden transition in the intensity of the image, because an edge detector detects sudden changes in energy. So here's your delta function. Consider the delta function, which is going to be delta of t, where t is equal to 0, will be equal to 1 in an instantaneous fashion. So where epsilon is very small, infinitesimally small, surrounding the delta function, that impulse, if you integrate across the impulse, it will have unit area. This is why the delta function is not really a function, right? Because it's more like a mathematical abstraction. So if you were to do convolution-based explanation of how sampling occurs, what you're doing is a time shift sequence of impulses across a switch which samples an input signal, and that is a kind of convolution. And that convolution does the sampling. So here you can sum up all of the samples that are done against an input signal. This one input signal is called X, and as you resample that signal, the output will be, we'll call it X of n. And that will change the spectrum of your input signal. And when we talk about the spectrum, what we really talk about are the partials that are used to create the original signal. And this is part of what's known as, in the biz, the Weierstrass approximation theorem. The Weierstrass approximation theorem says, and you've probably learned this in basic physics as the superposition principle, you can make an arbitrarily complex function by approximating it by adding up the basis functions. Got enough basis functions? Add them all together. These could be sines and cosines with different amplitudes at different frequencies, and eventually you can approximate as complicated a function as you like. Well, when you do that, you are doing what's called constructive synthesis. You're adding up simple basis functions like sine and cosine to get a relatively complicated looking function, arbitrarily complicated function. The inverse of constructive synthesis is analysis. When you do a Fourier analysis, what you do is you attempt to identify what the amplitudes should be of the different sine and cosine waves are for different frequencies. And those are the same sines and cosines that you'll need in order to reconstruct the original image. That's the analysis. So I have synthesis and I have analysis. And there's two kinds of synthesis, and the first kind of synthesis is the one where you take all the different sine waves and cosine waves and you add them together to make the arbitrarily complex function. And we call that constructive synthesis. And the second kind of synthesis is called destructive synthesis. And in destructive synthesis, what you do is you start with a complicated function and then you use filtering to remove some of those partials, to remove some of those sine waves and cosine waves. So two kinds of synthesis, constructive and destructive. There's the Weierstrass approximation theorem, which says using constructive synthesis and simple waveforms like sine and cosine, you can create an arbitrarily complex waveform to with any precision you like. So when you decide what those sines and cosines should be, they determine the power spectral density of the function, or what some people call the spectra. And so what that does is it describes the energy at different frequencies. And so when you talk about the spectra of the function, let's say it's voice, you say, gee, there's a lot of energy down at the 1 kilohertz range. There's very little energy above 2 kilohertz, because normal speaking voice, that is voice quality, telephony, really doesn't have much above, let's say, 3 kilohertz. And so when you are dealing with plain old telephone service, or what we in the biz call POTS, you're dealing with something that samples at 8 kilohertz, which means there's a cutoff so that nothing goes above 4 kilohertz, and they have filters that start at around 3.5 kilohertz and roll off gently, so that when you're going for a voice grade telephone line, you typically don't expect to have any frequencies in the spectra above 3.5 kilohertz. That's typical. So we establish through analysis the Fourier coefficients, and then those Fourier coefficients through constructive synthesis can be used to reconstruct the original signal. The original signal is on the left, that's V of t. The Fourier coefficients A0 through AN and B1 through BN, these are on the right. And then you just use different frequencies for sine and cosine in order to be able to get the reconstructed voltage as a function of time. In the continuous time Fourier transform, the way in which we do the analysis is we take the sine and the cosine and we create a complex number. And we say the cosine will be the real part and the sine will be the imaginary part. And we can use what's known as Euler's relation, which is on the lower part of the slide, in order to represent both the cosine part and the sine part. And now if you think about it, Euler's relation, e to the I theta, is nothing more than a vector in the phase plane. And if you look at a vector in the phase plane and you drop the apex of that vector down to the real part of the number of the imaginary plane, what you'll get is the cosine part because of SOHCAHTOA and the trigonometric laws. And if you take the apex of the vector and you project it onto the imaginary number line, what you're going to get is the sine part. And that's where Euler's relation comes from. And if the vector was non-unitary, that is, if it had a magnitude other than 1, there would be an r in there. It would be r e to the I theta equals r cosine theta plus I r sine theta. But in this case, we're using something with magnitude 1. Using sine and cosine as my analysis functions, I multiply by the input signal. And then for different frequencies, I can compute what the amplitude is at those frequencies for both sine and cosine. And that is how I do my Fourier transform. So, in a sense, a Fourier transform is nothing more than an integral with a complex exponential for the kernel. And that's it. That's a Fourier transform. And the complex exponential is done at different frequencies. And those are your analysis frequencies. Similarly, you can do the inverse Fourier transform with practically the same code. Another integral, only the kernel has changed sign. So instead of e to the minus I theta, it's e to the I theta. So Euler's identity is that's key for doing this. You could use a sine and cosine representation instead of using Euler's identity. That's legit. And if you wanted to, you could do this one harmonic at a time, doing what's called harmonic analysis. So for the nth harmonic, you can create a frequency that is n times the sampling frequency, and that will be, or n times what they're calling f naught in this case, and that will be a way in which you can create a kernel that doesn't involve using an exponential. But then you have to do it twice, one for sine and the other for cosine. And by the way, what's the difference between sine and cosine? Yeah, just the phase. 90 degrees out of phase. So, in fact, you need that phase information to do a proper reconstruction. And so here's your convolution theorem. Let's see, convolution is going to be a sliding window dot product. So this is how it's defined. In the continuous time domain, we're going to take the analysis waveform, W, and we're going to flip it around, do a piecewise multiplication, and integrate the result. And the convolution theorem says that multiplication in the time domain is equal to convolution in the frequency domain. Similarly, for image processing, multiplication in the spatial domain is equal to convolution in the frequency domain. So we got a few things in here that have been proved in the book, and I'm not going to torture you with them. But what happens at the end of the day is you get reproduced spectrum all the way across when you do sampling. And as a result of that reproduced spectrum, what you do is you put in a low-pass filter. And the low-pass filter is called an anti-aliasing filter. And aliasing removes the spectrum that occurs at harmonic intervals over the sampling frequency. So here's the summary. Convolution in the time domain is equal to this integral, the sliding window dot product with the analyzing filter reflected. If you want to do it in the discrete domain, you can do it with a summation. And that summation, I wish I could get my cursor to show, that summation is shown here at the bottom. And if you look at the top versus the bottom, the only difference is this integral got replaced with a sigma. And now we can see Microsoft Excel being used to do a piecewise convolution with a sliding window dot product. So here is G of u, some sort of input signal. Here's f of x, another signal. Now here is G of u, and it's flipped. So we flip about this initial point, and now we've inverted the sequence. and then we do a piecewise multiplication. 1 times 2 plus 2 times 1 gives me 4. Then I take this vector, slide it by one element, and now I have 3 times 1 plus 2 times 2, which is 3 plus 4, which is 7, plus 3 times 1, which makes 10. Then I slide this down by 1. This is what I mean by sliding window dot product. And what do I get here on the right? It's 3 times 1. Wait, 3 times 2, which is 6, plus 2 times 3, which is also 6. So 6 plus 6 is 12, and I would expect 12 to be in here. I hope. Well, it doesn't show it. I have to move it? Why is it 15? Is that correct? Let's see now. That's 2 times 3 plus 3 times 2. It should be 12. This doesn't look right. Let's cover it up. That way we won't see it. So now we got it in the two-dimensional domain, and this is just like the 1D version of the same thing, only with a difference. And the difference is we're doing it with doubly nested integrals, and down at the bottom it would be implemented with doubly nested for loops. Another sliding window dot product. So there is this term in the field called the region of support, which is indicating the area under a curve that's non-zero. And so when you start to move the kernel of your convolution across your image, presumably some part of that kernel will be non-zero. So your analyzing function will be expressed in a two-dimensional window which has been digitized. So if it were something like a Gaussian curve, you might say, well, geez, how am I going to do the Gaussian curve? Well, first you generate an implementation function for a Gaussian curve, which gives you a Gaussian value at every point, and then what you do is you resample that continuous Gaussian curve so that you can get the window of the desired resolution. So you have to, if you start with an interesting function like a two-dimensional Gaussian function, in order to turn that into a discrete image, you have to essentially resample that input function. And then you'll have a non-zero area inside of that window, and that'll be called the region of support. Does that make sense? I mean, think of it a different way. Suppose you wanted to digitize a sine wave. What would you do? Well, you start with math.sine, right? And then you'd say, geez, I wonder how many samples I need. You'd say, I need 200 samples. Okay, great. So then you make a dilation parameter that goes from 0 to 2 pi, and you go in increments of 1 over 200. And then for each increment, you populate some array that's 200 elements long. And that resamples the sine wave. So then you can start with an arbitrary function and then create a digitized version of it at arbitrary precision. Does that make sense to people? Sort of? Yeah. So, regions of support are interesting because when you take a Fourier transform, mathematically we assume we start at time equals minus infinity and end at time equals plus infinity. Okay, do signals start at time equal minus infinity? No, they do not. And do signals end at time equal plus infinity? No, they have finite extent. So in general, it makes almost no sense mathematically to assume that you can integrate from minus infinity to plus infinity. You'll have a finite area over which you can do your integral. In other words, this has to be a definite integral if you're working with real samples going in on input. So what you do, if you want to be able to sample things so that you can go off the edge of an image, for example, because you assume the image is replicating indefinitely, is you can either replicate the image a little bit so that when you slide your sliding window dot product, it goes off the edge of the image, or you do a wraparound and you come back to the left-hand side of the image as you slide off to the right-hand side. And they call that a cyclic convolution. And the reason that this makes life a little bit more complicated is because you don't want to get that array out of bounds at runtime exception that you were getting before when you were computing the standard deviation inside of your windows. So the way this works is you use the mod function in order to be able to go back across in order for the index to go from the left back across to the right. And it's possible to avoid the mod operation if what you do is you select a window which is of odd size. And the reason why is because an odd size window will always have an exact center. So if you have a 7 by 7 window, I can find the size. If you have a 3 by 3 window, I can find the size. If you have a 2 by 2 window, I can't have an exact size for this window traveling across the image. And as a result, the exact center, sorry, I keep saying size, I should say center. The exact center can't be found, and so I need to start using mod operations if I have an even-sized window. So to find the exact center of some window, I must have an odd size. That's the bird's eye lowdown on that caper. So what will the limits be if window G is a 7 by 7 window? Well, I go from minus 3 to plus 3, and then I can always make sure that I have, or minus 4 to plus 4 if it's 7, right? Because that's the size. Minus 3 to plus 3 if I start at 0. And then I can always make sure that I don't go out of bounds I don't have an array exception at runtime. I don't go out of bounds when I index into the kernel of the convolution. So if I can't find the exact center of the kernel, the analyzing function, then I've got a problem. I've got to use the mod operation. And so here's what happens if you go off the edge of the corner. Remember that sliding window dot product? Here's one that's looking like a 3 by 3. I want to compute this edge, this corner in the right-hand corner, right? I want to figure it out. Well, my 3 by 3 went off the edge, so it's got to wrap around to the top and grab pixels from there. So here's how I implement this if I can know the exact center of my kernel. And remember, it's just a sliding window dot product, so it's piecewise multiplication, and then you form a sum. And that's all I'm doing here. And then I clip the sum. Why do I clip the sum? Well, because I have a range. I don't like negative numbers for my pixels. Why? Because my image cannot be displayed with negative numbers. When I go to compute the image, it has to range from 0 to 255 in all the color planes, red, green, and blue. And if you ignore the image wrapping, here's what happens. You end up zeroing out the corners of the image, right? They just end up coming out unprocessed. So you start off with an image that's 256 by 256. You end up with an image that's like 250 by 250. You have to be able to grab off the edge of the image on the left-hand side when you're off on the right-hand corner, because otherwise your image is just going to generally be smaller when you're done. Loss of data. Cyclic convolution allows you to have an image output which is the same size as the image input. That's key. Another way to implement the cyclic convolution, you could take the image and you could just grab hunks of it and duplicate it. You could rubber stamp it going up, going down, to the left and to the right, and maybe into each one of the corners. And then you wouldn't need to use the cyclic convolution operations. But now you've grown the image. So there are a few different ways you speed up the convolution. One way is called Java Advanced Imaging, which is a highly optimized set of subroutines that you can call from within Java that are very good for small windows. Another is to do an FFT, a fast Fourier transform. Maybe hardware could speed it up. Add a systolic array with an FPGA or something fancy. Hit it over the head with a big hammer. Right? So, there's some opportunities for speed up, but this is one of those most often studied problems. And it's not particularly easy to speed it up. And what I found about Java Advanced Imaging is it eats my edges. And so I implemented a mechanism for doing Java Advanced Imaging with extra borders. I added the borders, and then I used the so-called MDI, which you see here today, known as the Multiple Desktop Interface. And so what this does when you open up an image, here's the knee, is it looks like there's a window inside of the window. And you can have multiple images opened at the same time. Here's the Earth. Yep. And it looks like you've got multiple things running at the same time, but in fact it's just one Java job in the taskbar. And here is the Gaussian panel, and now we can adjust the kernel width, and we can adjust the standard deviation of the Gaussian curve. And you can see how the image is getting smaller using Java Advanced Imaging, although it's reasonably fast. And now, by changing the size of the kernel, we basically shrink the image using Java Advanced Imaging. And if you want, you can leave a kernel at a given size and then change the standard deviation of the kernel. Isn't that slick? And if the image is in the foreground, like here's knee, then that'll operate on the knee image. And you can see the knee image has gotten a lot smaller as a result of the big kernel. So to make a kernel of different sizes, you want to start with a nice Gaussian function and then resample it in order to be able to create a kernel of the given size. Gesundheit. And you could find that in the blur menu item under Gaussian panel. It's a kind of low-pass filter. How am I doing here? Good? Everybody sort of follows along? Oh, and it's also busy printing in the background. That'll slow you down. So here's my little Gaussian filter. Let's see how that looks. So a Gaussian filter looks like it has something called make kernel. Now to make the kernel, you have to remake it every time you change the radius. How is this working? Takes the square root, gives me r squared, and then it uses an exponential, and then divides through by the square root of sigma times 2 pi. So that's like an ugly way to express an elegant Gaussian function. And you re-sample this elegant Gaussian function, which is continuous, in a matrix in order to create your analyzing function, your analyzing window, and then you do your convolution. But you've got to redigitize that Gaussian function for every time you change one of the basic Gaussian parameters, including the standard deviation, including the size of your kernel. Does that sort of make sense? There's a little computational overhead in doing that, but there's not a whole lot of choice in the matter. One of the things that's related to convolution is called correlation. And you may have already seen this. The correlation is a sliding window dot product, just like the convolution, only with a difference. And the difference is you're not reflecting the function. So when you look at f of the exampled operation here on the right, you see it's moving across J. But if you look at f on the bottom, it's moving across J after it's been reflected. The operation of cross correlation is represented by the cross with the circle, and the operation of convolution is represented by the asterisk. These are not straight multiplications. Why do I want a cross correlation? Because if the analyzing function f is a template that you're looking for, then when it sees that template, it'll give you a resounding yes. So if you cut out a little chunk of something you're looking for, like the eyes, let's say, in the mandrel, and then you grab the eyes as a template, you can take the eyes and drag them across the image, and it will say, yes, I found the eyes, and they'll start glowing. So you can make the mandrel have its little eyes glow because the cross correlation is able to identify templates. If you have something of correct scale, let's say it's a tank, and you're looking for tanks in the forest because you want to see troop movements or something or other, you can scan for tanks. You could scan for V2 missiles and find the Nazis. Think of all the applications. As they're fond of saying in entrepreneurship, the possibilities are endless. So if you want, you could find terrorists. Ooh. Right? Just imagine if you were using this for face recognition and you wanted to find, they had these things, what do they call them? Playing cards out in the field, and each one of the playing cards that they were playing with had the picture of a terrorist on it. And people became very familiar with the terrorist's appearance because they were fighting a non-traditional war where terrorists didn't just dress up in uniforms and march lockstep and say, aha, I'm the enemy. So they had to try and identify the enemy by memorizing their faces. But if you had face recognition, right, this would allow you to do that in an automagic fashion. Yeah, they were playing cards in Desert Storm, and the playing cards had pictures of the 52 most wanted terrorists. Well, they'd play the playing cards, but in the process of manipulating the playing cards, they kept looking at the faces until they became ingrained in them. Yes, sir. Can you find Waldo? Sure. Yeah, we could make that a homework assignment. You wanna find Waldo? Yeah. This was a thing called the border frame. Well, this is what I had for homework at one point, using a slider to dynamically alter parameters. I can show you how this turned out because I actually ran this for homework at one point. Let's see if we can get this to work. I will bring up an image, Control O, open the image. Let's find an airplane. Here's an airplane. Now let's use the border frame. Border panel. So now what we'll do is we will zero out the image here. Now suppose instead of zeroing out the image, we put in a constant. That'll work. You can copy the image, so that takes the last row and copies it up. Or you can reflect the image, and now it's reflected. And I could put in a left border, and a right border. And now you can kind of see what happens when you put a border in the image that's of the same size as your matrix. If you put a border in the image that's of the same size as your matrix, you'll be reducing the image to something which is the same size as the original image. So you start with a image, then you take a border image which does the reflection, and then instead of using what's called cyclic convolution, you grow the image. And now you can just process the larger image, make a smaller image, and then that smaller image will be the same size as the original image because you grew the image before you did your processing. You see. Does that make sense? Sort of? Right. So now I've got it. Now I can do a 100 by 100 window analysis. Here it is with the wrap instead of the reflection. And if I just do that 100 by 100 analysis, it'll chop off all the borders, because that's essentially the only thing cyclic convolution does, is it causes the image to be wrapped. So I've done the wrap already. Now I've made the bigger image, and now I can do image processing on it and not have to worry about losing the borders because they're really not needed in the output image. So now when I apply the process and I decide that I want to do Gaussian thingies, let's see, make this right. I can eat away at the border and make it as large as I like, and then I just take out the chunk in the center because that's the only part I care about. And it doesn't matter that it shrunk this image around the edges. Right? That doesn't matter because those were just replicated pixels anyways. And in theory, I could have gotten my kernel width to go above 40. I could have gone to 100, and it still would have left me with an image in the center that would have been fine. So that allows me to avoid the cyclic convolution. But it's pay now or pay later. If you're going to do a whole bunch of convolutions with a big image and it's going to keep eroding your edges away, it makes sense to do a border image first. Otherwise, cyclic convolution makes sense unless the image is so large that you're better off doing this kind of convolution with a fast Fourier transform, in which case that'll be the fast way to go. Lots of ways to do the same problem. Isn't that fun? How educational. So I'm going to insist that you guys read the book. Chapter 4 and 5, that's a done deal now. Actually, we finished chapter 8 as well. And what was chapter 7? I forget. I gotta look. Bear with me just a moment, please. Chapter 6 and Chapter 7 were input streams and file readers and writers. So at the end of the day, we skipped the hardcore Java part and just did the image processing part. So I did the homogeneous point processing chapter. That's a done deal. Histogram equalization, you guys have seen it. You've done it. That's it. Did the introduction to digital image processing, explaining the eye and the optic nerve. So you've seen that, and you can certainly read about it. And then I got into what's known as direct convolution. And it's direct convolution because we didn't do any Fourier transforms to do the implementations. We just used the definition of convolution, the sliding window dot product, and then either we used Java Advanced Imaging to accelerate it, or my own code with cyclic convolution, or border-based convolution. So you guys are done. I think you don't need a homework other than the reading. And for the reading, I really must insist that you read Chapter 4, Chapter 5. It's a lot of reading, actually. And but you know, I think you were supposed to read Chapter 4 already. And then and Chapter 8, which is direct convolution. So really, Chapter 8 is your new chapter, and that's pages 175 to 191. So it's not too many pages. Plus, I don't think the math is too bad, and everything that's explained in there we went over in class. And so then for next time, we'll be doing spatial filters. We'll get back into the median filter, which we saw today. I gave you the little introduction to blurring just by doing a little blurry stuff, but we'll talk a little bit more about it. And then we'll do edge detection. So we're doing, you know, when you do low-pass filters, we call it blurring. When we do high-pass filters, we call it edge detection. So that's, I mean, it's kind of a term of the field, I guess, when you do image processing. And so that'll give you a good introduction to some elementary image processing. We'll call it low-level image processing. Low-level meaning at the pixel level. Okay? Any questions? You got your reading assignment? All right then. Stay warm. Have a good evening.